Hi, welcome back. In today's tutorial, we're diving into brain tumor segmentation using YOLOv11 and Python. And we will start by training segmentation model on a brain tumor dataset, then move to running inference to detect and isolate tumor regions from medical images. And we will divide the prediction process to two steps. One will be more straightforward, and the second one we will learn how to extract and manipulate the result from the prediction process. This tutorial is part of this segmentation playlist, so you're welcome to watch more tutorials using other tools in order to segment computer vision tasks. So let's run a short demo and explain what we are going to do in this tutorial. We would like to generate a model for our custom dataset. In this tutorial it will be a brain tumor segmentation. We will use this dataset, and you can see if I open several images, for each of those images there is annotation that segment the tumor area in the image. So if we go back to the code, first of all we will create a model that runs for all those thousands of images, and after that we will run a prediction, and we'll do it in two methods. The first method will be using the out-of-the-box prediction and display the result. And in the second options, we will give us more flexibility to decide what to extract out of the prediction. And first of all, this is the first result. You can see it's displaying the original image along with a bounding box and a colored area of the tumor. This is the out of the box. But what if we would like to extract the full mask out of the image, or maybe if there are more than one mask and we would like to extract only one of those masks? So I will guide you how to create a second option of prediction and segmentation. On the right side it's the original image, and on the left side you can see how can we extract the mask and generate a binary mask of a grayscale image. And all the codes will be provided in the video description. Here's the code for the prediction. So let's move on for the installation. Let's start with the installation part. I will do a short brief of this file. Install YOLOv11, and first of all we will create a new Conda environment. As you can see here, the name will be YOLOv11 3.1.2, and it will be based on Python 3.12. Of course you can choose your own custom name for the environment, but please keep it this Python version 3.12. After that we will of course activate, and now we have to install the PyTorch library. First of all, you have to find what is your CUDA version. If you don't have a GPU card, you can also install the CPU version. If you run this command, you will find what is your CUDA version. Mine is 12.8. I believe you will discover that you have 11.x or 12.x. And in this tutorial I am using PyTorch 2.7.1, and let's jump to the PyTorch website. And if we go to this page, which is installing the previous version of PyTorch, I decided to in this tutorial to use this version 2.7.1. and you can see here for each CUDA version what is the command, the installation command for installing the 2.7.1 PyTorch. So this is the command for CUDA 11.8, and this is the command for CUDA 12.6, And of course there is a command for a CPU only. If you don't have a GPU card, you can install PyTorch running on CPU. So after you install, I just copied the command for 12.8 and put it here. So this is the command for 12.8. After installing the PyTorch, you should install YOLOv11, which is under the Ultralytics library. And in this tutorial I am using the current version, which is 8.3.176. I prefer that you would install the same version so we can get the same results. After the installation, when we go back to our IDE, I am using VS Code, we have to change or move to our new Conda environment. So in order to do that, you have to press Ctrl, Shift and P, and this menu will pop up. Now we have to choose Python Select Interpreter, and now you have to find, you will get a list of all the environment that are currently installed in the Anaconda. Here it is. He put it the last of the list, but here it is, YOLOv11 312. So now all the code that we will run will use this environment with all the installation. Now let's continue to the next step, and the next step is downloading our dataset. I will leave here step number 1, download dataset txt file, and this file contains the link for the dataset and several more instructions that we will cover right now. So first of all, let's copy the link and go to our browser, and here you can see our dataset. It contains about 800 images that already divided to train, validation and test. If for example we will open one of the images and click here on the left side on the word tumor, you can see that the area was already segmented, and this is the target of our tutorial. We will build a model that learns to segment tumor and brain images. Let's move to another image, and you can see here this is the segmented area for the training. This is another image, and this is another image, and all the images contain already annotation for the tumor. So let's go back to our list. Let's go back, and if we click here on the download dataset button, we have to choose download dataset because we would like to work locally. So let's choose download dataset, click continue, and now there is a combo here for choosing the format of those annotations, and we will choose YOLOv11. So choose YOLOv11, and here you should choose download zip to the computer, and let's click continue, and it will start downloading. I already done it. Basically it's a zip file. I already download the file and put it on one of my local folders, as you can see under dataset, object segmentation, brain tumor, YOLOv11. And if you will open the zip file, you will see that it contains 3 subfolders: train, validation and test. And if we go through the train folder, it is composed of images and labels. Let's go to the images, and you can find here all the images from the train folder. And if we go to the labels, each of the images have the same name with a different suffix named .txt. And if we will open one of those files, you will see that it composed of the first character is the category, and since it's a binary segmentation, means there is a tumor or there isn't a tumor, so we have only one category, and all those numbers indicates the dots around the tumor. And if we have one tumor, you will get basically it's a one line, it's just fragmented. But if we have more than one tumor in the same image, once again we will have the character 0 and a bunch of numbers that mark the second tumor. So for example, in this file indicates a tumor in one image. What else? If we go back to the folder, we can see that we have the same concept in the validation images. So here are the validation images and the labels of those images, and the same for test images. There is also a YAML file that I will cover in the next step. Now let's go to the next step, and the next step is generating the YAML file. I can copy the YAML file from our dataset, but let's create it by ourselves. It will be more clear. So let's create a new file. Let's name it config.yaml. And first of all, we have to define the path, and the path is indicates where we store all the images. So I will just copy and paste the path to our dataset, and please notice that the path is for the main folder. So under this folder we're expecting to see the train subfolder and the validation subfolder. And next, let's define the train, and the train would be under a train subfolder, and all the images are stored under the train subfolder. Next, let's define the validation. So basically it's the same concept, valid underscore images. Let's go back to our folder just to double check it. You can see this is the full path to our dataset, and under that we have train and valid, and under those subfolders there are the images. It automatically will grab the labels if we will give it the path to the images. And finally, we have to define the number of categories, since it's a binary segmentation, meaning if there is or there isn't a tumor, then the number of categories is 1, and we can choose a name for this category, and let's name it tumor. This will be the name. And basically we finished defining our config YAML, and we are ready for the training. Let's save it. So now we are ready for the training. So let's build our model and write the code for the training. So it will be step number 2, train.py. We will start with importing ultralytics, and we will import the YOLO object. Next, let's define a main function. We will start with loading the model, and YOLO, and here we will use the YOLOv11 large model. So it will be YOLO11, L for large. There is a nano, a small, a large, and an extra large. So we will use the large for this tutorial, and we are using a segmentation project, so it will be segment.pt. .pt is the suffix for PyTorch. So this basically will load the pre-trained model. Next, let's define a project. So project is a folder where we are going to store all the results. So let's put it under the temp. Of course, you can use your custom folder, and it will be, let's call it Brain Tumor Segmentation. Great. After that, let's define an experiment. Experiment, it's basically it's a subfolder under the project folder that can give us the ability to run multiply training on the same project. So let's define an experiment. Experiment equal, let's call it my model L for large. Let's define a batch size. The batch size is depends on your hardware, your GPU card. I prefer to run it on 16. If you have let's say a strong GPU card, you can put here a higher value. The batch size influence of how many images will be loaded for each batch, so each epoch will run faster. Now let's define the data YAML, the one that we just created in previous step. So let's go to the config YAML, and I will just copy the relative path to this YAML file. Since I'm running on Windows, I will change the direction of the slashes. So my YAML file is stored here. Of course, you can put the full path to your YAML file. Now let's add all the arguments for the training. So it will be model.train, and the first argument is our data YAML. Next, let's define the number of epochs. Let's start with, I hope that 50 will do the job. Then the project argument, we will get the value of our project variable. Next, it's the experiment. The experiment is called name in the list of those arguments. Now it's the batch size. Great. Device is if you have several GPU cards in your machine. Since I have only one, I'm choosing device equals 0. 0 is the first one. Image size will be 640. All the images will be converted to this size for the training. Patience, let's put here the value 5. Patience means that the training will stop if there was no improvement during 5 epochs. So if there is no improvement, we will not wait for 50 epochs and we will stop earlier. Next, verbose true for login. Next argument is validation equals true, and this tells the training process to run validation on the validation dataset at the end of every epoch. Now at last, let's add the if statement in order to run the main function. Now let's start the training. First of all, we are downloading the YOLO segmentation model. It runs automatically. And next, it starts loading the images. Here are the train images, 583 train images, and now it's the validation images. And let's start the training. I will move for a fast forward so you can see the progress. And I believe that we will wait only for the first epoch and the second epoch. I believe that the process will take several hours, maybe 2 hours, 3 hours. So let's jump directly to the end of the training. So after several hours, the training has finished. You can see here that it ran through all the 50 epochs. And if we cover the segmentation loss, we can see that the value is going down through the training. We will see the result in a few minutes. And everything was stored in this folder. This folder contains all the information, all the result information. And let's go to this folder. And here it is. In this folder there are many images. First of all the weights are stored in this subfolder named weights. There is 2 files here, last.pt and best.pt. Last.pt contains the weight of the last epoch, and best.pt contains the weights of the best one from all the training. Let's go back and let's open first of all the result.png. Let's focus on the train and segmentation loss. You can see that the values are going down, and this is a very good sign of the training. Let's close it and let's open another file, and let's for example open the validation batch 0 prediction, this one. And you can see here that during the training it took the first batch of the validation data, and it's trying to do the prediction of the tumor, and you can see here that it will find the tumor in the images. Now let's test our model with one of the test images. So first of all, let's create a new Python file. Let's name it step 3, predict. We will import YOLO from Ultralytics so we can load our trained segmentation model. Also, we will import OpenCV and NumPy. Next, let's add the path, the saved path. This is the path to the best weight from our training run. Make sure the path match your experiment folder and file name. Great. Now let's point to a single test image that we want to segment. So let's go to the list of the test folder. So here are all the test images. The model never saw those images before. Let's grab this one and let's copy the full path of this specific image name Y192, and all the rest is a long name. So this is the full path for the image. Now let's load the image using OpenCV, and after grabbing the shape of the image, let's load the fine-tuned YOLOv11 segmentation model from our disk. Now segmentation option 1 will be run inference by passing the image string. Setting save true tells Ultralytics to write a visualization of the results to the runs directory. And this is like a quick win when we want to automatic overlay and save the image for us and display a quick result of the image. Let's run the code and let's see the result of segmentation option number 1. Great, so here is the image and here is the tumor. So in this solution, it's an out-of-the-box solution. You can run the segmentation, the prediction, and display the result. Now let's continue to the second option that give you more manipulation and configuration during the prediction. Now let's run the segmentation in a different approach. We are passing the image as NumPy array and pull the first result since we only sent one image, the object exposed boxes, masks, class score, and more. Get the mapping of the class ID to class names from the model, and next let's create an empty grayscale mask to accumulate per object mask into a single image. And after that we extract the predicted class IDs from each detected object and print it to the log. Let's run the code. And here you can see, here's the list of the classes. And here is the predicted in the specific image. So in this specific image we have one tumor which it's indicated with the value 0 because we have only one class, so 0 indicates a tumor. If for example our image contain more than one tumor, we will see 2 zeros in this result. In the next phase, we will loop through each predicted mask and process it. We'll log the class for each object and save an individual mask image too. We will move the mask tensor to CPU, convert to NumPy, and scale to 0 to 255 for saving and visualization. After that, we will convert the class ID tensor to a Python integer and print a friendly message with the class name. Next, we will resize the mask back to the original image size in case the model used a different input. We will combine the current mask into the final mask using a max operation. This preserves any foreground for previous object without double adding values. And after that, we will build a per object file name and write the individual mask to disk for debugging and logging. And at last we will save the accumulated segmentation mask for the whole image. Let's run the code. So this is the first one, let's close it. And now you can see the result of the second segmentation and prediction. First of all, here you can see the original image with the tumor, and here you can see a mask that was extracted out of the image. So we did a prediction, we identified the mask, and we grab it out of the image. So the second options give us more flexibility of extracting mask out of the images after the prediction. So thank you very much. I hope you enjoyed this tutorial. Bye bye.